There is an idea regarding why gravity might behave differently to standard thinking or differently to the classical theory of Newton and Einstein. So this is still a bit speculative, but basically the idea is that the classical theories of gravity do not include any quantum effects.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
The world needs evidence-based public policy now more than ever. Making the right decisions should not be partisan politics. Please help spread The Rational View by going to patron.podbean.com/therationalview. Together, we can make a better future. Hello, and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. In this episode, I'm going to get into some science for you, astronomy. I'm digging into a recent announcement from the astronomy community. This is based on data from the Gaia satellite, which is sitting at a Lagrange point, the Earth-Sun L2 Lagrange point, and taking high-precision measurements of the position and velocity of billions of nearby stars, mapping the local galaxy. Researchers have been using this data to test the theory of gravity and understanding whether the stars are orbiting the way they should about the center of the galaxy. And more specifically, testing modified Newtonian dynamics, which is an alternative theory which modifies general relativity to describe gravity and to describe rotation curves of galaxies. This theory was developed to explain away the need for dark matter. Dark matter was originally postulated to account for anomalous rotation curves of galaxy. If you measure the light-emitting matter in a galaxy and you measure the density of that and use that as a proxy for the mass of the galaxy, you expect a certain gravitational rotation of the outer regions of the galaxy. But observations show that the outer regions of the galaxy are moving too fast. MOND suggests that gravitational acceleration actually stops dropping off as fast as normal when the acceleration due to gravity drops below a particular threshold. The competing interpretation is that there's some dark matter out there which interacts only through gravity, which is, you can't see it, but it's causing these outer stars to speed up. So researchers have analyzed the rotation curves of tens of thousands of widely separated binary stars or orbiting each other in the Gaia dataset, and they believe that the data support MOND over Newtonian gravity. This is a huge announcement, and it's been picked up by the science media, and their results seem to provide a high degree of confidence. The press coverage seems to suggest that this is a smoking gun that decisively overthrows Newtonian gravity and general relativity all at once. If this is true, it's huge. Why are the authors not packing their bags to Sweden as we speak? With a little digging, I found that other researchers are looking at the same Gaia dataset and have come to the opposite conclusion, and they believe that the data supports general relativity over MOND. What gives? To understand this discrepancy, I'm interviewing a skeptical astronomer on The Rational View. Dr. Indranil Banik did his undergraduate at Trinity College, Cambridge, before moving to St. Andrews for his PhD with Hongsheng Zhao, where they worked together on Milgromian dynamics, or MOND. Dr. Banik then went to Bonn for a Humboldt Fellowship with Pavel Krupa. He returned to St. Andrews in 2021 and spent his first year back on a detailed 150-page invited review on all aspects of MOND. He's been working on the wide binary test since late 2017. He organized the 40th anniversary celebration of MOND conference in St. Andrews in summer 2023. Among other results presented here, conflicting results were presented on the wide binary test, and there was intense controversy surrounding whether the results indicated a failure of Newtonian gravity at low accelerations. Dr. Banik, welcome to The Rational View.
Hello.
So, from your bio and your publication history, you're certainly an expert on MOND. Could you provide us just a brief interview of what MOND really is, and maybe contrast it to the prevailing theory of gravity?
Sure. So MOND is a theory that as you get further and further from a point mass, instead of following the usual Newtonian inverse square decline of the gravity caused by that point mass, at some point it becomes a more gradual inverse distance decline. So that's the main thing. But the other crucial thing is that the distance where this occurs depends on the mass, because the important threshold is not distance in this theory. The important threshold is one of acceleration. So once the acceleration gets down to some special threshold called A naught, which is approximately the gravity exerted by a galaxy in its sort of outskirts, then that's where the transition occurs. So that also explains the difference with the standard theory.
Right. So MOND, I think, was proposed as a purely empirical response to observations of the rotation curves of galaxies. So the outer stars in galaxies were rotating too fast based on what we knew of their mass distributions from looking at all the bright stars that we could see. And using Newtonian mechanics, general relativity, Einsteinian gravity, we would have expected the speed to slow down more than it seemed to be slowing down. We could measure these rotations and we could see they're slowing down. Is there a good motivation for MOND other than just this? What else does MOND predict, or why would the accelerations change at a certain threshold?
Okay, there is an idea regarding why gravity might behave differently to standard thinking or differently to the classical theory of Newton and Einstein when gravity becomes very weak. So this is still a bit speculative, but basically the idea is that the classical theories of gravity do not include any quantum effects. They're literally sort of classical or non-quantum theories. But as you get to a lower and lower acceleration, the gravitational field contains less energy density. So any gravitational field can be thought of as that region of space-time having some energy density associated with the gravitational field. Now, at some point, if you have a sufficiently low acceleration, then the energy density that corresponds to becomes smaller than the energy density in the so-called dark energy. The dark energy is a substance thought to explain the accelerating expansion of the universe. And the most sort of conventional interpretation of this is that it's a 0-point quantum energy density. So basically, a minimum energy density imposed by quantum effects, because any quantum system has a non-zero sort of ground state. I see. Yeah. So the idea then is that if your energy density is so low that that it's below the dark energy density, then quantum gravity effects would become important. So it's that's the. And I should also explain that numerically speaking, where this transition occurs, in terms of your gravitational field having less energy density than the dark energy, that is within an order of magnitude of the A naught acceleration threshold in MOND. This was realized many years after MOND was first proposed, of course. But nowadays, that's one possible explanation to your question.
Now, the acceleration we're talking about is extremely low.
Yes.
Acceleration from gravity on the surface of the Earth is like 9.8 meters per second squared. Yeah. This is what we're used to here. The A naught threshold that we're talking about is something like 0.1 nanometers per second squared. Is that correct?
Yes. 0.12, yes.
So orders and orders and orders of magnitude less than what we're used to here on Earth.
It's also less than the gravity experienced by any of the spacecraft we've sent. So even compared to the Voyager 2, it's about 3 orders of magnitude below that.
Wow. Okay. And now I've heard it said that, so MOND, obviously general relativity is a theory that's stood the test of time. It's been well demonstrated over a century now.
Only in certain regimes.
Sorry?
Only in certain regimes.
Yeah, okay.
I mean, in the solar system, it certainly works extremely well. And near black holes, some tests have been done recently where it works extremely well. But if one were to straightforwardly apply general relativity to the rotation speed of a galaxy, for example, obviously that doesn't work. So the standard narrative that general relativity passes all the tests, that's only true if you ignore all the times it doesn't pass.
That's true, because the dark matter is basically could be thought of as a failure of general relativity to explain the rotation curve of a galaxy.
Certainly, it can't be considered a success of general relativity.
So I've heard it said that standard theories of gravity are required to explain cosmology and the primordial distribution of atoms and deuterons. Is this a failing of MOND, or are there
no, it's not. It's
explanations for that?
Well, no, it's not a failing of MOND. What one has to understand is that MOND doesn't actually do very much in the early universe because, for example, the accelerations are very high then, and therefore the modification I was talking about wouldn't actually come in.
I understand, but if you look at primordial theories of the formation of deuterium and higher elements
we wrote
from
in
fusion.
Detail about this in one of my papers about the primordial nucleosynthesis. There's no reason why this should occur differently in MOND. Basically, the background expansion rate history would be the same as in the standard cosmology.
Okay. I thought it needed the dark matter to be some real gravitating thing for that to happen.
Dark matter doesn't come in the Big Bang nucleosynthesis era.
Okay. Though that's good to know. I've just read that people have complained that it doesn't, that cosmology doesn't agree with it, but maybe
there might be other aspects of cosmology where that might be like a reasonable sort of thing to say. I would suggest that the distribution of large-scale structure is still a bit hard to understand in MOND.
Okay.
Yeah. But the Big Bang nucleosynthesis is typically not raised as an issue.
There's been a lot of new discoveries made by the James Webb Space Telescope on the primordial universe. Do you think that the results that we've seen are supportive of MOND or not at this point? Or do we have an opinion at this point?
I would suggest they do seem to imply galaxies formed very quickly, and in general, a stronger amount of gravity at low accelerations would help, because basically the MOND effects come in after redshift 50. So between redshift 50 and 10, MOND could have significantly accelerated the formation of the first galaxies. But on the flip side, though, if MOND were correct, then galaxies would not have dark matter halos. And without the dark matter halos, it can be that makes it harder to form galaxies. So at the moment, our results actually indicate that without the dark matter component, even if you do have the MOND gravity, galaxies actually form much slower than in the standard model, which leads to a catastrophic disagreement with the James Webb observations. In MOND, galaxies only formed by redshift 4, according to our results.
Interesting. So
this was
you've been a leader in the field of MOND as an alternative to the standard gravity. But that being said, you published a paper in 2021 looking at wide binaries and the Gaia data, the Gaia satellite. And the conclusion of your paper was that Newtonian physics appears to be sufficient to model the orbits of nearby wide binaries to a relatively high degree of confidence.
Yes, the 2021 study was a detailed sort of planning document about how the wide binary test should be done. It didn't make any strong conclusions by itself. There was a study I did in 2019 which tried to put in place some of the methods that should be used for the wide binary test. But this was before much of the modern Gaia data was available.
Could you describe the wide binary test a little bit for everyone?
Yes. So the wide binary test relies on the fact that MOND is an acceleration-dependent theory. So for a galaxy-scale system, one would have to go many thousands of light years out in order to enter the so-called MOND regime. But for a star, one would only have to go out approximately a tenth of a light year. And then one would already be in the MOND regime. So the idea of the wide binary test is to use binary stars with separations that exceed a tenth of a light year in order to test whether the MOND hypothesis is correct. So in detail, in the solar neighborhood, wide binary stars should orbit 20% faster than the Newtonian expectation if they are in this sort of MOND regime.
Okay. So you've looked at this, and there's a recent paper that's come out that has gotten a lot of media attention out of Korea, looking at tens of thousands of these wide binaries from the third release of Gaia spacecraft data, and they are basically saying that this confirms MOND, or requires MOND to something like 5 sigmas in terms of their result. And I think you have come out and said that you're skeptical of this result. Could you maybe describe what you think is wrong with this work?
Yeah, so we're actually working on this just now, and working on like a resubmission of an article that we submitted in March to. And this time, yes, we have identified like a fatal problem with the analysis of Che 2023, which is related to the uncertainties in the relative velocities. So essentially, there is no proper quality cut associated with how precisely we know the relative velocity between the two stars in a wide binary, which is critical for the wide binary test. If this quality cut were handled properly, the sample size would drop it will drop only a little bit, but we've identified that the signal is no longer there in this scenario. And we're hoping to resubmit the article with this crucial addition within a month.
I see. So there's some contamination in the data, some uncertainty.
However, these are random uncertainties that are officially published as part of the Gaia catalog. We're not inventing any new source of uncertainty.
The difficulty in the wide binary test is Gaia provides position measurements of stars that you can use in parallax to tell how they've moved transversely, and it also provides Doppler measurements to tell whether they're coming towards you or going away.
Yes.
Does it give you both those things? Both those, and from those you can get a 3-dimensional velocity of the stars, but then you have to figure out where the plane of the orbit is on the sky.
But this is not such a major deal, because one does it statistically. So one assumes a random inclination, and sort of statistically can compare the distribution of velocities with the predicted distribution.
I see.
The problem I was describing is related to the random measurement uncertainties. Basically, if there's a certain spread of velocities, then the spread is broadened further by measurement errors. And this preferentially happens at low accelerations, which can mimic a MOND signal.
So it's kind of a Poisson distribution. You're at the low end, and the error is biased in one direction.
The error would almost certainly be biased in one direction. And the main reason is that the Newtonian velocities are very small. They become small at large separations. So the same uncertainty in the velocity in meters per second corresponds to a larger uncertainty in the velocity divided by the Newtonian velocity, which is the key parameter for the wide binary test.
So alas, you don't believe this is supporting the MOND hypothesis. As a as a leader in this field, does this mean that MOND, if these wide binary tests come back, is it coming back inconclusive or is it coming back negative against MOND?
Well, it's coming out strongly against MOND in favor of the Newtonian expectation, because what happens if you do the quality cuts more rigorously, either in our own sample or have a much better understanding, or if you take the sample of Q, which he lent us, but you apply an additional quality cut to basically restrict to systems where the velocity data is accurate enough. Either way, the results very closely follow the Newtonian expectation, even into the low acceleration regime. There is no sign of like a break in the gravity law as would be expected in MOND. And the 20% excess, by the way, that is supposed to happen is strongly rejected by the observations.
Wow.
Yeah.
Okay.
So we have approximately 16 standard deviation confidence in this result.
Wow, that's huge. So in terms of the theory of MOND, is this putting a nail in the coffin then, or are there potential other ways out that we could save MOND?
So we have explored that a little bit in our study. What I would say is the wide binary test obviously is probing gravity on very small length scales compared to galaxies and larger structures. If one were to invent some additional mechanism beyond just the traditional MOND with an acceleration scale, in which also the effects are somehow suppressed below a certain length, then one could circumvent the wide binary results. Certainly, this was not expected a priori, and I would say that it doesn't rule out galaxies sort of following MOND, but it makes it much less likely. And also, it's not clear like how one would be able to construct such a theory. Like how one would get a small-scale suppression of the MOND effects.
Now, looking in my rigorous research on Wikipedia, there's mentioned something called the field effect.
The external field
MOND.
effect.
Is that so what that says is if something is in a strong enough gravitational field from an external object that's not part of the system you're analyzing, it will suppress the MOND effect. Is that a possible contributing factor here?
It's definitely a contributing factor. The problem is it's something we've already taken into account in a great deal of detail. I should say, first of all, the magnitude of the external field on the solar neighborhood now carries negligible uncertainty because recently the acceleration of the solar system relative to distant quasars was directly constrained by the changing aberration angle. So the quasar's light is deflected slightly due to the Earth's solar system's motion. And this angle changes every year because the solar system is accelerating.
That's great.
Yeah, so because, and also it matches other expectations based on our rotation within the galaxy. So we know how quickly the local solar neighborhood is accelerating towards the galactic center, or even in relatively distant quasars, we know it, but the two results are much the same. Yes, this definitely weakens the gravity binding sort of wide binary stars. This is why you only get a 20% excess to the Newtonian expectation. Without the external field effect, it would be much higher. In fact, it wouldn't be a fixed percentage. It would sort of rise as you go to larger and larger separations, sort of without limit. But the external field effect, however, is already taken into account in detail in the calculations I was talking about.
I see. So, I mean, MOND is certainly an elegant and beautiful theory. I'd hate to see it destroyed by ugly facts. The hints of quantization in gravity. I'm not a cosmologist or a relativity person. Is relativity and quantum mechanics have obviously had problems getting along in the past. Are there were there promising avenues for bringing them together through MOND, or is this something that hasn't been explored very much?
There have been a few studies which postulate a certain they postulate that quantum gravity works in a certain way, and they reduce to a MOND limit at very low accelerations, in addition to recurrence of GR-like behavior at higher accelerations. MOND doesn't offer, it's an empirical sort of equation, but using that as a constraint on how to construct a quantum gravity theory has helped a little bit with some of the attempts to unify GR and quantum mechanics. So it has been somewhat helpful. But,
so this is interesting. So you are basically deep into the MOND field. You've worked a lot of your career on MOND, and now you come up with this observation that the stars just don't show it. Does that mean there's going to be no MOND celebration next summer?
In my opinion, the likelihood of any other researcher organizing a similar MOND conference is very low in the foreseeable future. Certainly, I wasn't going to do that anyway because I'd done both this one and the previous one in Bonn 4 years back. I don't know if obviously anyone else will want to organize such a thing, but I would suggest the likelihood of another similar event being organized is very small.
Yeah, it's quite a roller coaster ride because you go on the popular media and this result is being trumpeted as proof of MOND, which is a huge Nobel Prize winning discovery if true. What was there a problem in the peer review, do you think, or was it a good paper that just had some unexpected issues in it, and has the media made a mistake in blowing this up the way they have?
So I think there were some mistakes at various stages. First of all, the expert observer who was advising Q about this had significant reservations about the data being used in this way for the wide binary test. But instead of listening to these concerns, the lead author simply made do without any co-authors. So he had no support whatsoever for his claims in terms of from other people. However, obviously he thought that the evidence supported his claims. Right, obviously. But there the problem was perhaps, as you say, with the peer review, because the issue I was talking about relating to the relative velocities, obviously one basically has to combine or add up in quadrature the uncertainties of the motion of each star and compare that with the relative velocity kind of thing. Yes, I guess the referee didn't notice this issue, which is actually unusual because when I was talking about it with other people, we didn't realize it immediately at the conference, but very shortly after, not only myself, but several other observers that were advising me also noticed this issue. So I don't know why the referee wouldn't have noticed that. So basically what Q did is ask for the velocity in the reference frame of the sun to be accurate at the 1% level. But that doesn't guarantee that the relative velocity between the two stars in each binary is that accurate.
Sure.
So yes, perhaps it's a failure in the peer review process. I would suggest, though, that the media perhaps were not too much at fault in this scenario because there weren't any obvious problems that the media could easily have noticed with this article. Once it got past peer review, I'm sure there was only one author, but it's not that easy to see what the problem would be.
But there are other papers out there analyzing the same measurement which reached the opposite conclusion.
Yes.
And I don't see a lot of discussion of that in the media.
I think the one thing the media could have handled a bit better is there wasn't any plot showing some easily computed, like observable quantity, what it does in the Newtonian case, what it might do in MOND, and showing like a difference. So kind of look at the overall velocity distribution, in other words, and trying to say what does that look like in Newtonian mechanics? What does it look like in MOND? What does it look like in reality? This is what the other paper you mentioned by the group of researchers in Queen Mary does do that in a lot of detail. Yes, so indeed, like this should have been mentioned by the media, perhaps. That would have helped, but it's still, nonetheless, it would have been very difficult to find what was wrong with the results of Q.
Yeah.
In my opinion.
No, it seemed, I was very excited when I read it, and I was like, wow, this is amazing, and now I have to look into it. And I didn't hear from the astronomy community the sort of generic or general acceptance of this. Like I heard skepticism. I saw your articles or people quoting you in the news saying, well, let's be very careful about this.
So I gave a lecture about this like in March, explaining our submitted article. And yes, I guess the people have been quoting that a little bit, which is fine, because the results seem not to have changed very much. But yes, it's not widely accepted. And the main reason perhaps is that there's no sort of easy way to analyze the observables that will let you sort of see that MOND works better. In his article, however, if one were to try and analyze the data to show such a thing, actually it would be relatively easy to come up with such figures. This is why I'm saying it would be extremely difficult for the media to notice the issue. It's actually not. It's actually related to the quality cuts.
Well, that's fair. So you're preparing an article that rebuts this or takes a look at the problems. When do you expect to have that published?
So we submitted it in mid-March, and we're working right now on addressing referee comments, but also addressing the analysis of QJ. And this should be submitted early next month, I'm hoping. Resubmitted, I should say. And yeah, we're hoping this should be out this year.
Okay, well, very interesting. Well, thank you for your time in helping to explain to us the interesting field of modified Newtonian dynamics, and perhaps the end of modified Newtonian dynamics for now, until someone comes along with a better idea to explain these binary results. So very surprising. This was not where I expected us to end up this interview, but thank you so much for sharing your expertise with us and helping us to understand what's going on. For spending your time chatting with us, I'm going to send you a Rational View t-shirt. So thank you so much, Dr. Banik.
You're welcome.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/therationalview. Thanks for listening.